Okay, fine. Thank you. So, so far what we have seen, so starting from the syllabus, so what is thermodynamics and some physical properties and heat characteristics of the fluids we have seen, and mixer properties we have seen, and we have defined zeroth law of thermodynamics and first law of thermodynamics, and first law of thermodynamics we have applied to the control volume. Okay, and then we have defined second law of thermodynamics. Then in second law of thermodynamics also we have seen Kelvin Planck statement and Clausius statement, and both of them, how both are coinciding, how both are conflicting together, so that we have seen. Okay, that was the syllabus. We have done good job in the exam also. Now we have a great scope to define certain other parameter through the second law of thermodynamics. That property or parameter, that is entropy. Okay, so for all the cycles and all the processes, we can apply this concept of entropy. Okay, so we are telling it is the property. Just now I already have mentioned that it is the property. Then why it is the property? Okay, so those all we are going to see. So by now itself, you might have come to understand when you are seeing your data tables. What all are there in the data tables? Along with specific volume and enthalpy in the table itself, you might have seen in the last two columns entropy, yes. Okay, so that means it is state property. Yes. So, but anyhow, many times I have mentioned over there what is this entropy and all. Let us see in the further chapters. Yes. So now this is the time to see about that. So here we have defined actually dq by t, the ratio of dq to t. This particular parameter we have defined mathematically as entropy. Okay. So certain definition kind of thing we don't have for this, as like suppose specific heat. What do you say specific heat? The amount of heat required to raise the temperature of 1 degree of certain material is called specific heat of that particular material. Yes, such a definition you can give. Here we don't have such a definition. Okay, it is defined mathematically and proven mathematically. Okay, so that is this dq by t. This dq by t you can apply for all. All means irrespective of whether it is reversible or irreversible. And also we have classified our thermodynamic cycles into two broadly. What are those? Heat engines and refrigerators. Okay. So this concept of entropy, whatever dq by t, you can apply for reversible cycles or irreversible cycle, heat engines or refrigerators or heat pumps. Okay. Now let us see. Now here by defining dq by t as the entropy, and also it is defined for case of engines. This is the engine, right? What is the engine? It is taking heat from high thermal reservoir and rejecting to the low thermal reservoir. Through that, certain amount of work is coming out from the system. Okay, that is the engine we have defined. Yes. So for this engine, particular engine, here it is defined over here. If you observe over here, less than or equal to G, 0. Okay, less than or equal to 0. How it is happening? Let us see. Okay, these two we have to see now. So from this cycle, what you can understand, this is the high temperature reservoir sucking heat of QH. This is the low temperature reservoir and rejecting the heat of QL. The difference between QH and QL is work anyhow, but same time that is the heat transfer actually. Yes, delta Q equal to this minus that. Yes. In that case, that is obviously greater than 0. Yes, it is greater than 0. And in one condition, what condition it is? If both this reservoir as well as this reservoir temperatures are reaching to the same, okay, reaching to the same, then what will happen? The delta Q would be ceases. That means delta Q value would be 0. Okay. But reverse cannot be possible. Okay. DL is higher than TH. It is possible when, if you assume that as refrigerator or heat engine, sorry, heat pump. But here we are considering it as heat engine. In case of heat engine, the forever possible condition is this TH is much greater than this TL. Okay. But however, the possible condition is these both are equal. Okay. In case of heat engine. In that case, what you can define this delta Q, whatever is there, either greater than 0 or just equal to 0. Fine. Okay. If you understand that, then let us go further. Now
Sir,
let
if
us, yeah,
work done reversible equal to 0, then
pardon?
sir, if W reversible will be 0, then it can be equal to 0, not QH minus QL. So equality sign will be there now.
W, I'm not getting you actually. This is
Sir,
0.
yes, sir. Then it should
Yeah,
be.
that is 0 means these both are 0.
Oh,
Means not
okay.
0. These both are same.
Yes, sir. Got it.
These both are same, but engine should be working. If engine is not working, even this is high, this is low, that doesn't matter. You have not on the engine. Okay. So if it is 0 means obviously these both are 0 when engine is running. Okay. It doesn't run also. If both are same, even though you trying to on it, it will not on. But that is actually not the feasible situation. Okay. Idealistically, that is not the feasible situation. However, theoretically can be possible. We cannot contradict that. It is impossible. Okay. So that's what always delta Q is greater than 0. Okay. Otherwise, it can be equal, but it cannot be negative when you are considering it as heat engine. Okay. That is about delta Q. Now, let us go further. How can we get this ratio? So, what are we considering here? The engine, we are considering it as reversible engine. Okay. Then eta means efficiency equal to 1 minus QL by QH. Yes, in our previous class itself, we have defined it. Yeah, 1 minus QL by QH. The same time, the same eta equal to 1 minus TL by TH. Yes, if it is a reversible engine and it is Carnot engine. Okay, so then 1 minus QL by QH equal to 1 minus TL by TH. That way, ones will be getting cancelled, minus will be getting cancelled. Okay, once you shuffle Q and higher terms and lower terms either side, okay, then you will be getting this. That means if it is the reversible cycle, dq by dt equal to 0. Okay, if it is the reversible cycle, dq by dt equal to 0. Fine. So far, what we have proved, for any heat engine, dq, mere dq means only dq is greater than or equal to 0. For reversible cycle, so far we have proved dq by t equal to 0. Now let us see irreversible cycle. Okay. Many irreversibilities are included over there. That is the reason what you can conclude here. You can conclude work of irreversible is less than work of reversible, obviously. Because apart from delta Q, certain other energy is also getting wasted because of its irreversibilities are involved in that. That is the actual cycle. Okay. Then instead of these terms, we are directly substituting its negative terms. Okay, means heat terms. Sorry, not negative terms, heat terms. Okay, but anyhow, source is the same we are considering. Okay, source is the same. Rejection source. Why we are considering source is the same? In case of the both the engines, you are burning same fuel at same stoichiometry. Okay, and same mass flow rate of the fuel. Mass flow rate of the fuel means same thermal input you are providing to the engine. Okay, that's what we are considering. QH as the same. That could be any engine, gas turbine engine or thermal power plant or IC engine. Okay. Now only where the difference is coming, these rejections. Okay. These rejections. If it is a reversible engine, rejecting, that means wastage of the heat is low. If it is irreversible engine, wastage is very high. Yes. That is only we are telling over here. Wastage in the irreversible engine is greater than wastage in the reversible engine. Okay. So that way, what we have proven over here, dq by t equal to less than 0 in case of irreversible. Then what we have proven so far, dq by t would be greater than or equal to 0. Sorry, dq, only dq is greater than or equal to 0. dq by t is less than or equal to 0. Okay. This we have proven for if it is heat engine. Similar way, this is only anyhow, this is the conclusion of that. Okay. Similar way, we are working upon refrigeration cycle or heat pump. Okay. So what is there here? Same philosophy. You no need to worry about something new over here. Only thing is some other places negative would be coming, some other places positive would be coming. Okay. So see, the cycle itself is different than that cycle. Here we are providing the work and sucking the heat from the low and supplying to the higher. Yes. That is only because of that only from where you are sucking, this is your room. Where we are throwing, that is environment. Where we are sucking, room is at 16 degrees centigrade. If you set your refrigerator, air conditioner, where you are throwing, that is 50 degrees centigrade. If it is Gujarat or Rajasthan, yes. So for that you are supplying energy from your power socket. Okay. So these terms are negative, positive terms are changed. Okay. So if same procedure, whatever we have done for the engine, if you repeat that, you can get this. Okay. You no need to worry about that. So earlier what we have considered? Earlier we have considered QH as the constant. Okay. Rejection QL is different. Yes. See over here. Yes. This QH for both the cases are equal. Rejection QL is different, and that's what here greater than symbol. And here what are we considering? QL for the both are same. Okay. This QL is both for same. Rejection would be something different for reversible engine and irreversible engine. Okay. That way. Then we have defined this. This you can see because the heat engine I have explained in detail. This refrigerator or heat pump you can read by yourself. Okay. That is. Now let us see what we have seen over here. If it is reversible engine, dq by t equal to 0. If it is irreversible engine, dq by t should be less than 0. Negative value you should get. Is it? So here actually one small problem is required to solve to identify that. Okay. So that is the thing we are considering over here. Okay. So what is this cycle? I think you might have already identified what is this cycle. This is steam power plant cycle. Many times we have discussed about this. Okay, at that time actually we were following other book. This time actually I'm changing my book. I'm coming back to this Sontag. Why? Because the whatever the central team is following even this book to means to solve the problems in the exam. Okay, but anyhow concept is same. Whatever the book we are following. But however, for your convenience, myself I have changed my textbook also. Now I am following Tank. Okay. So there, this figure is a bit different. This is the boiler. Okay. This is the pump. In the boiler, actually, is the heat transfer, constant pressure, heat addition is happening, constant pressure and constant temperature. Why? When we can consider constant temperature? If we are injecting the steam at saturated vapor, superheating we are not considering. Okay. And here, this is the condenser section. In the condenser, what is happening? Constant temperature, heat rejection. Then only your vapor is converting to the liquid. Then in that case only this pump will be able to pumping back to the boiler. Okay. These two, this is the example we are considering. In this example, actually, we have given many values also. Okay. These all values also. Now what we need to check, just dq by t. Since this is the irreversible cycle, the dq by t should be less than 0. Okay, that we are checking. See, what can we do? This is the integral, cyclic integral of, why we are applying cyclic integral means this is cycle, right? Total cycle we have. That is the reason we are applying our dq by t. Here, wherever heat transfer taking place, because why we can neglect this? See, this turbine expansion process is isentropic expansion actually. Okay, isentropic expansion. What is isentropic expansion? No entropy change. Why? Because this is adiabatic process actually. Adiabatic process we can call it as isentropic process. No heat transfer over here means no heat losses over here. Okay, idealistically. And this pump also adiabatic compression. Okay, that's what here. These two we are not considering since Q terms are not involved over here. In these two, since no heat losses or no heat additions, these Q terms we no need to consider for these two items. Here Q addition is there. How? We are burning the fuel, that heat is transferring to the fluid. And here heat rejection is there. How? We are passing the steam through the condenser coils where water is circulating, that heat is rejecting to the water. Yes, we have seen many examples also. Okay. That's what these two process only we have considered over here. Okay, then this is the summation of dq by t of boiler plus dq by t of condenser. Okay, so here this T we can take it out. Why we can take it out? Here is just now I have mentioned this process we are considering as constant temperature and constant pressure heat addition. Okay, that means superheating is neglected. If superheating is there, pressure would be constant, however, temperature will be rising. Yes, so that we have neglected. This is saturation temp means constant pressure and constant temperature heat addition. This is constant pressure and constant temperature heat rejection. Okay. Those two we consider. Since temperature is constant, we have taken it out. Okay. We have taken it out. Now, this is this integral, we can apply the limit. What is that? Process 1 to 2. This is 1 to 2 is the heat addition up to this, not only required up to here, we can take up to here also. This process, total boiler process. Okay, 1 to 2. What is the heat addition in the 1 to 2? What is the heat rejection in the 3 to 4? Okay, up to here. This point you can put here also or here also, but not after the pump. Okay, these are. And these in the problem, whatever the problem actually I have not pasted actually. Okay, that is the value. Once you consider it as unit mass, okay, then H2 minus H1 is this much. And at that particular location, this is the temperature, okay, and in the condenser, the enthalpy difference is this much, okay, and that temperature is 53.97. Once you substitute this all, then we will be getting minus 1.087 kilojoule per kg Kelvin. Okay, this is the minus value absolutely. That is only we are telling for case of irreversible engine, cyclic integral of dq by t should be less than 0. Okay, this This is the example actually considered from the textbook. You can consider any other example, any other exercise problem. You can apply this concept like this and you can check it. Okay, fine. Now, so far, before starting the class, what we have mentioned, entropy is a property. Yes. What work we have identified? Work is the path function that we have defined in our previous classes. Okay. Whatever the path it is following, the area under the path is defining the quantity of the work. Yes. If path is changing, then obviously area will be changing and quantity of work also would be changing. And here, let us see the entropy, whether it is a path function or point function. Okay. So now we are considering it as a reversible cycle. First, we are considering 1 to 2 flowing by A and 2 to 1 coming back by B. Okay. This is one. For that, we have written the cyclic integral of dq by t equal to 0. Why? It is the reversible cycle, right? It is a reversible cycle. If it is a irreversible cycle, it is obviously would be less than, right? So these two we have considered. Then integral 1 to 2, since it is the process, dq by t of A, and integral 2 to 1, since it is the process, through the B. Okay. Now the same thing we can consider, instead of going from going through A from 1 to 2, let us consider another process going through C. Okay, like this, and coming back through the B. That is also giving you this thing. Integral 1 to 2 of C, dq by dt of C, and coming back, right? So dq by dt of B. Okay. So obviously, for a cycle, if it is a reversible, dq by dt equal to 0, that is the reason this total thing and this total thing we are equalizing. Okay. Then whatever common thing is there, b dq by dt, dq by t of B, these two terms are getting cancelled and these two terms are getting equalized over here. Okay. Equalized over here. From that, what can we say? From point 1 to 2, whatever the process we are going, even this process or this process. Okay. That is only change of the position. Okay. Change of the state. Okay. By following any process, it doesn't mean actually. Okay. Once state is changed, then property, then the value is changing. That is the reason we can call it as the property. Okay. Therefore, it is the property. In case of the work, what will happen? If the process is going from 1 to 2 by following A, this total area would be coming. Yes. If process is going from 1 to 2 through process C, this small area would be coming. Okay. The work difference is there. Since it is the property, whatever the path it is going, that doesn't matter. The wherever it is located, that is only the matter. Okay. That is the property we are considering. So since it is a property, what can we say? From obviously, if it is at point 1, it has certain value. Yes. Yes, like pressure P1 means 1 atmosphere. This could be at 50 atmosphere. Okay. Like that, here it has certain entropy S1. Here it has certain entropy S2. Okay. This could be gain or loss. That is another issue. Okay. Like that, here the change we can call it as ds. The ds itself is S2 minus S1. Okay. That we are considering. Fine. So obviously, since it is the property, you have seen many things from your many properties you have solved according to the mixer principles. Yes. In our problems also, by seeing your tables as well as by following EES. Okay. So we have obtained for different dryness fractions. Yes. Enthalpy we have calculated at different Raynaud's fractions, internal energy, specific volume. Is it? So same like that. The same formulas we will be using for calculation of entropy also. These are okay. SF plus SFG. Okay. That is about that. And here actually once after entropy is defined over here. Okay. New kind of plots you can plot. So for what plots we have seen? PV diagram means pressure volume diagram we have seen. Then what you have seen? HT diagram, enthalpy temperature diagram you have seen. Okay. Then PT diagram you have seen. Okay. So like that, since here entropy new term is defined over here, then enthalpy and entropy. This kind of plot you can get. Okay. And even temperature and entropy. This kind of plot you can get. Okay. So this whatever plot you have over here, this enthalpy and entropy, right? It usually called Molle diagram. Okay, Molle diagram. Please remember this. That is with the name of a great scientist, German scientist of Richard Moelle. Okay, this is Moelle diagram. So anyhow, in further classes, in further chapters, we are going to work upon this and we are going to solve many problems also. Okay, these are the two different plots. Once we have defined or identified this property, entropy new property, two different other plots along with PV, PT. Okay, these two also added. Now the same thing. Let us see. Already you know what is a Carnot cycle. Okay, from the Carnot cycle itself, we have defined efficiency that is giving you eta equal to 1 minus QL by QH, or otherwise, since it is the Carnot cycle, we are defining in terms of the temperature, then 1 minus TL by TH. Okay. So this entropy concept also let us apply to this. This is very easy, nothing more. Okay. So far, you have seen Carnot cycle in certain different way, like this curve, and this curve, this curve. Yes, curves kind of thing. Now, once entropy is defined over here, you can see this kind of rectangle box for the Carnot cycle. Yes, this is what is happening here. If you take here previous example, whatever we have solved a small problem of power cycle, okay, like steam engine, sorry, steam power plant cycle. This is the boiler, okay, constant temperature, heat addition. Then this is the turbine. Okay, what is happening over there in the turbine? Adiabatic process. What we can call the adiabatic process? Isentropic process. Means change in the entropy is zero. That is the reason this is the TS plot. This is temperature and this is entropy. Change in the entropy is zero over here in the turbine. Then again this is the condenser. Okay. And again condenser is working what? Constant pressure, heat rejection, constant pressure, constant temperature. Simply phase change. Okay. And again what is this? This is the pump. And what we have considered a pump also? Pump also we have considered adiabatic compression. Is it? This is adiabatic expansion. This is adiabatic compression. Okay. That is also adiabatic process itself is a isentropic process. So this is also vertically straight line. So that way your Carnot cycle you can see in different shape upon your TS plot. Okay. Then obviously whatever, what is the total amount of heat supplied? QH is area below 1, 2. Okay. This total thing. Area below 1, 2 is heat supplied. Okay. Then area below 4, 3. Just area below 4, 3. Here. This part is heat rejected. Okay. Then whatever this is your work output. Yes. So this is in terms of this thing only we have defined here. So for this case actually entropy change is there S2 minus S1. Okay. Okay. S2 minus S1. For this case delta S equal to 0. For this case S3 minus S4 will be existing. This is S3 minus S4. Then for next case, delta S equal to 0. Yes. Okay. That we are defining over here. This is also, you know it very well before that. Now, in terms of entropy, we are going to define certain other equations. This you know very well. Yes, this you know. What is this? Your first law of thermodynamics itself. Yes. Now we have defined another property, that is entropy. Entropy equal to dq by t. We have considered from where this thing. Yes, dq by t. That means wherever dq is there, delta q, you can simply put ds, change in entropy multiplying by temperature. Yes. Okay. So instead of that, we are dq wherever it is there, we are substituting tds. Okay. Then you know anyhow, work equal to PV diagram, area under the PV diagram. Yes. Area under the PV diagram itself is the work. Once you substitute these two terms in our equation, then it is this first equation. Okay, TDS equal to du plus VdV. Okay, now we know one thing, enthalpy. Okay, as like entropy, enthalpy also has no definition. As like specific heat, whatever I have given definition. Okay, in one of our class in certain particular slide, we have defined enthalpy is a parameter, that is internal energy plus PV. Yes. So now instead of this U, we are substituting this also. Okay. That means dH equal to, so here these all are derivative terms. Yes. dH equal to du. Then this is derivating in terms of two variable parameters, PdV plus VdP. Okay. So wherever your du is there, this net term we will be substituting over here. Okay. That way, one equation we can derive this, and second equation we can derive this. Okay. These equations actually we can call it as Gibbs function or Gibbs equations. Okay. These things we have to remember. So this is actually this chapter entropy. We still have certain discussion. Okay. So if we define or if we discuss more and more, then you will be confused. That is the reason we have concluding, means we are concluding over here. Okay. So now I would like to ask you one question. Since we are considering it is the reversible cycle, and here entropy is the constant in case of turbine as well as constant in case of the pump. But actually, perfect adiabatic process is not existing. Okay. In that case, this 3 point will be shifting this side or that side. Okay. Then this 1 point will be shifting this side or that side. Okay. Can anyone answer me? This point number 3 is coming here or here by your concept, whatever we have understood. Can anyone answer? Think about that. Think about that. I'm giving you 2 minutes. So could you able to understand, or otherwise could you able to come to one point? What is happening here? The point 3 will be marching towards this or towards this, or point 1 will be this side or that side. Can anyone answer now? Okay, no problem, no problem. Think about that. Okay, think about that. If it is not ideally adiabatic process, okay, this curve starting from 2, 3 should not be a straight line. It would be one slightly curved profile like this, or it would be slightly curved profile like this. Yes, sir. That means the point number 3 would be going over here or here. Okay, so according to that, where it should go by following whatever this physics we have over here. Okay, so answer me tomorrow morning, no problem. Think coolly. Okay. Okay. So nice. Tomorrow, rest of the topic let us discuss. Okay, upon the entropy. Then on the Friday 2 classes, let us solve some problems upon this very clearly. Then let us move to the application of entropy or second law of thermodynamics upon the control volume. Okay. Then the second law of thermodynamics part would be completed. Okay. Yeah.
Sir, I had one doubt. Like in the mid-sem exam, I got 0 marks. Like
Oh, really? Who is talking? Apurva Tejasvi.
yes, sir. But I submitted the paper. I solved it. I don't
Total
know.
zero you got. Total zero.
Yes, sir. I got 0 marks.
Let me see. Let me see. Let me see.
Also, I have mailed you the solution.
Oh, what is it?
Three
So,
triple zero seven, sir.
what is that
AG
number?
20 AG 30007.
For AG. Okay, 20 AG. This is actually 20 AG 30007, right? The problem is, I think you have not entered your email ID, name, these all the things. Okay, your answers also not noticed in. Do you able to see here? Yes.
Yes, sir. But I have given the answers. I don't know why. I entered the answers.
Entered the answer.
And name email ID was also entered, I think. Sir, if it is possible, can you please take a retest?
This is only like this is see unmatched. Wherever unmatched is written, right? This unmatched means your roll number, your these things are not matching actually. You might have answered. The data is there. Okay, but it is coming unmatched. Okay, whatever unmatched things are there, that we left actually.
Uh, so then can you
And
please like
even this guy also is that 20 AG 30039. Okay, and here this is yours, right?
yes, sir.
Okay, okay. So
Yes, sir. I'm 20 age.
20
I'm
AG
20 age
39.
30039. Yes, sir.
39. May I know your name?
Sir, Vidhu Vikas Singh.
Vaibhav Vikas Singh.
Vidhu Vikas Singh.
Okay, okay, okay. So you also please write one message, either in
Yes, sir.
mail or otherwise. Pardon?
I already mailed you.
You already mailed me. Let me see then. Let me see. Okay, Mihir Raj, our TS will respond to you. Okay, it may take some time, little time. They have identified my mail. Who is